All right, so begins Lecture 19 in General Relativity. And so here I am looking at Chapter 8 in Carroll. Oh no, Carroll lost an L. That's not good. Yeah, I wonder how many times I've done that. Oh well, I try. So I suppose as a personal side note, I don't really believe any of this stuff. Just so you know, like I think there are some large themes that are correct, but I think that largely speaking, it's a lot of wild speculation for the most part. Now, you only need to pay attention to cosmology for about, I don't know, a decade or two, and you'll find out that they'll change their story, radically. And so I'm not I'm not of the school of thought of taking them too seriously, but these are fun ideas to think about. So let's look at them. I mean, I do think there are aspects of truth in what we're doing, but I don't view any of them as sacrosanct, let's say. All right. Anyway, the fundamental principle that sort of underlies all of the major cosmological models discussed in Carroll is the Copernican principle, which he puts sort of glibly as it doesn't matter where you are in the universe, it should all be the same, kind of, sort of, something like that. So there's two aspects of that, isotropy and homogeneity. Isotropy is based at a point, right? So you're at a point, and if you can look any different direction at that point and they all look the same, that's isotropy. So like a cone, for example, if you're at the nexus of the cone there, the point, the vertex, any which direction you look, it looks all the same, right? From the cone, because every which way you look out, there's just a line that goes on and on, If you can imagine yourself as being living inside the surface of the cone. And homogeneity is when it's kind of got the same structure at each point, let's say. And so an example of a space with homogeneity would be R cross S2. This is also known as no, that's not Einstein's. This is R cross S2. Now this would not have isotropy at any point, because at any point there's a distinction between the point that's along the real line and the point which is in the directions which are in the direction of the sphere, right? You can kind of, in your mind's eye, imagine this as like taking the real line and gluing a spherical bubble at each point. But then somehow imagine that those bubbles aren't overlapping. So good luck to you. But anyway, so this is an example of space which is isotropy. This is an example of space which has homogeneity. If you put these two things together, you get a space which is maximally symmetric. And so the larger point in here is space-time is not maximally symmetric, because there is, in fact, a difference between the past and the future, right? Like, this was not always assumed. I mean, starting into all this, before the Big Bang came along, it's always been the philosophical wish of naturalists that there is no beginning to the universe, because if there's no beginning to the universe, you don't have to explain where the beginning came from. Unfortunately, the Big Bang models and viewpoint on cosmology has forced a little bit more introspection on where the universe came from. So it's just always been here and it's always the same, it turns out not to be a viable viewpoint in view of physical observation. But it certainly was the desired cosmology by, for example, Einstein at the start of all this. But in any event, we're going to be looking eventually here towards the end of this lecture at spaces which are maximally symmetric in the spatial sense, but not maximally symmetric in the temporal sense. So, but for the start of the lecture, we're going to look at maximally symmetric spacetimes, of which there are three, one of which you've already seen. Let's see here. Just as a backdrop, in the context of maximally symmetric space, the Riemann tensor has a particularly simple form. It is this difference of products of wow, it's just algebraic in the metric. There's not even a derivative term. Wow, man, that's simple. And here the kappa is r over n times n minus 1, where that's the dimension. So like in 4, this is r over 12. I was reading the corresponding notes from my professor, undergraduate, and he mentions that this was known. I think he says in Aaron. Which book did he say it was known in? Oh, Eisenhardt. He says Eisenhardt has a proof of this. And if memory serves me correctly, Eisenhardt is a differential geometry book from like Riemannian geometry book from like, oh man, I want to say like 1910 or something. So, I mean, this was known from the start of things. And anyway, so the first example of a maximally symmetric space-time is just Minkowski space. You have, this is your metric, your curvature is 0, your Ricci scalar is 0, your kappa is 0, and the Riemann tensor is 0. Zeros everywhere. Perhaps more interestingly, and I think this is, setting physics aside, this is an interesting, I think there's some interesting exercises here. So I think this is going to be some of your homework, because I think these calculations would be fun to do, and something concrete that maybe would be a good thing for you to have calculated. So anyway, let me just get to it here. So de Sitter space is the way to form de Sitter space is this. You can take I'm sure there are other ways, but so the examples 2 and 3 of maximally symmetric spacetimes, the way they're going to be formulated is by starting with a 5-dimensional space and then imposing an equation. So if you take one equation in 5 dimensions, to reduce 1 degree of freedom, so you're left with a 4-dimensional object. This is the easiest way to define a 4-dimensional space, by an equation. And so in 5-dimensional Minkowski space, right, you look at this 4-dimensional slice defined by minus u squared plus x squared plus y squared plus z squared plus w squared equals to alpha squared. Here alpha is a constant. And you can put coordinates on this. You can parameterize this 4-dimensional space according to these formulas. So the coordinates on the 4-dimensional space are t, chi, theta, and phi. Did I get that right? T, chi, theta, phi. Yeah, 4. And here's the 5 equations, which would be good exercise to like try it out. Plug these into here, see if it works, And not just that. Start with the Minkowski metric, which would be minus du squared plus dx squared plus dy squared plus dz squared plus dw squared equal to 0. Not equal to 0, but equal to ds squared. Start with the 5-dimensional Minkowski metric and see that when you substitute in these equations, it simplifies to this. So this is the induced metric on the 4-dimensional space, which is obtained simply by plugging these equations into the Minkowski metric. I think that's an interesting calculation, and it's worth doing. It's not terribly difficult. It's a little bit tedious, but I think it's worth it. I think you should do it. So, in other words, homework, explain this formula. All right, not so much explain this. These are just identifications. That's the metric on the unit sphere, and this is the metric on the unit 3 sphere. Although maybe it's worth understanding those as well for yourself. Like that might be a good homework to do. Whatever it takes to make those make sense to you. This is very postmodern homework. Do whatever it takes to make the story authentic for you. Doesn't sound like me. All right, anyway, so Carroll explains, as we can see, that this space is topologically R cross S3. And the way he explains it is by looking at the conformal diagram. And you can read about the conformal diagrams. I don't really have much to say about that, except that they're these like cute little pictures you can draw to understand. It's like a flashcard for your space, right? It's like a really quick, this is what the space looks like in terms of its causal structure in some sense. But anyway, because of that, he's able to identify that de Sitter space is really topologically just R across the 3-sphere. And this is Einstein's static universe. So basically time goes on, and at every point you've got, you know, 3 maximally symmetric, you know, you can go the same way in all 3 directions. All right, anyway, moving on. Then there's also anti-de Sitter space. So this one's interesting and different in its construction. A little bit surprising, really. He begins with R5 with the 2-3 metric in the sense that it's not the Minkowski metric, or you could say it's kind of like a Minkowski metric where you've got 2 time dimensions. So you've got minus du squared minus dv squared plus dx squared plus dy squared plus dz squared. And you study the 4-dimensional space defined by this equation. So minus u squared minus v squared plus x squared plus y squared plus z squared equal to minus alpha squared. On this space, which is called anti-de Sitter space, you can put coordinates t prime, rho, theta, and phi defined by these equations. And by plugging these equations into the 5-dimensional 2-3 metric right here, they will simplify to this. All right. And interestingly, again, that's a good homework problem, right? So like work that out, okay? And let's see here. And by work that out, I mean explain how this formula comes from these formulas over here. Let me scooch down a bit. This formula comes from these formulas substituted into this formula. All right. So, you know, mathematicians, we get very sophisticated about how to write metrics in terms of spaces and domains and everything, but there's a certain beauty to just, you know, plugging equations into equations and working through the, you know, the heart of it, which is what the physicists tend to do. Because all that pullback stuff, it's really just a notation for formalizing the process I just told you. Namely, to plug these equations into the metric and see that they simplify to that. All right. So Carroll explains, again by studying the conformal diagram, that the space is topologically R4. And here's an interesting tidbit, with infinity taking the form of a time-like hypersurface. So it's not the same R4 as Minkowski space, right, in terms of its temporal structure. Like, it doesn't have the same conformal diagram, whatever that means. Now, I think the reason that Carroll's going into these details is really just an excuse to motivate a discussion on the hot topic of the ADS-CFT correspondence. So this is anti-de Sitter space, this is conformal field theory, and it's a very interesting chapter in the saga of string theory where it was discovered that you could do calculations in anti-de Sitter space, or you could do calculations in quantum field theory in a particular sense, and that they're mirrors of one another. If I recall correctly, you're able to do, oh goodness, I wish I could remember. One is perturbative, one is non-perturbative. They were actually able to calculate things that they hadn't been able to calculate before using this correspondence. And I don't know whatever came of it, but there were a lot of people interested in this, to the point of I saw nuclear theorists who didn't care a lick about, you know, grand unification or anything like that, But they were interested in this part of string theory because it was perhaps a new way to calculate things in the nuclear physics, which they held dear. So I don't know. I should look back into this and see where it's gone to. I don't know. This book was written in the early thousands, which is about the same time I was in grad school, and so whatever's happened with the ADS CFT correspondence, it's not going to be in this book, unless he's updated it. But I don't think so. But I mean, probably Carroll has a public speech about it somewhere. It's not like he's not active, right? I mean, he's definitely involved in public science communication, right? So, anyway, I haven't looked into it. That's all I'm saying. But it is an interesting story nonetheless, the ADS CFT correspondence. Now, so what's the relation of Minkowski space, de Sitter space, or anti-de Sitter space to gravitation? So if we go back to the formula that was already due to Eisenhart, and we plug in 4 dimensions, we get this, which then, when we work it out, we get actually 3 kappa g mu nu. And so this means that the Ricci tensor is proportional to the metric tensor. When that happens, it's called an Einstein space. And oh yes, I need to read that paragraph. This is horrible. This is horrible. Oh my goodness, this is so horrible. Listen to this. Listen to this. It's like physicists. Oh, they're the worst. Look at this. So, the Einstein static universe is not an example of an Einstein space, which can sometimes be confusing. What is worse is we'll encounter later the Einstein de Sitter cosmology, which is not related to Einstein spaces, the Einstein static universe, or to de Sitter space. It's like, golly. Well, I mean, it's just Einstein, right? What did he not do? So there's our formula for the Ricci tensor. Let's move on here. So we found that our mu nu is that where the Ricci scalar is 12 times kappa. For maximally symmetric 4 manifolds, namely Minkowski, de Sitter, and anti-de Sitter, we have the Einstein tensor is just minus 3 kappa g mu nu. And so Einstein's field equations give us that the stress energy tensor is minus 3 kappa over 8 pi g times g mu nu. And of course, this is really, physically unreasonable for most purposes. It's weird to have a stress energy tensor which is everywhere constant like this. Well, not constant, but proportional to the metric, I should say. And but there are contexts where this is relevant. He says that this is the formula for stress energy tensor for vacuum energy, or for the cosmological constant, in which case you'd understand the density or minus the pressure to be equal to 3 kappa over 8 pi g. And in particular, physically speaking, if the density is positive, you get de Sitter space. If the density is negative, you get anti-de Sitter space. Anyway, Carroll explains these spacetimes are not consistent with observations for cosmology. However, they do serve as sort of ground states for GR locally. They describe general relativity in the absence of matter and gravitational radiation. So this is, like you said, kind of the background solution. And, well, anyway, more on that cosmological constant as we go on here. So that brings us to a more physical class of metrics, namely the Robertson-Walker metric. The Robertson-Walker metrics are based on the idea that the universe can be foliated into space-like slices such that each slice is maximally symmetric. So topologically, space-time is basically R cross sigma, where sigma is a maximally symmetric 3-manifold. So if we use d sigma squared for the metric on sigma, we have, for the Robertson-Walker metric, sort of the blank template of what it looks like. It should be minus dt squared plus r squared of t d sigma squared. Here r of t is a scale factor, whereas d sigma squared we can expand in terms of gamma ij, the spatial metric, in terms of the co-moving coordinate system here. that's one of the interesting things about this whole discussion is that, for all the talk of there not being a universal, you get used to these, jarring statements about the lack of simultaneity in special relativity, twin paradox, all that fun stuff, and then you get to cosmology and people start talking about the age of the universe, and you're like, what? What do you mean the age of the universe? You just got done telling me about how time isn't universally meaningful. How you talk about the age of things? So the answer, roughly speaking, is that there's this global frame of reference that's given to you by these cosmological models, the co-moving coordinate system. So with respect to that co-moving coordinate system that we all share, supposedly, you can compare times of different objects in different places, assuming that these models are reasonable. So that really bothered me as an undergraduate, just the disparity in claiming time was essentially meaningless. Well, not meaningless, but it was simultaneity, one clock to bind everyone by, that wasn't something you could do in special relativity. I mean, if you're going to do, well, anyway, that you necessarily had to have a discussion about who's moving with respect to who and how they're moving, in order to make sense of the time. And and then all of a sudden we're talking about the age of things. It bothered me a lot. But they do have an explanation, and it is bound in the really the existence of the Big Bang and the supposed co-moving coordinate system, right? Anyway, so the next page or so, Carol works on developing the necessary structure of d sigma squared, and given the maximally symmetric, maximal symmetry of the sigma, I'll basically follow along his calculations. They're very similar to ones I did already. So here's a go. So this 3 is for that it's the three-dimensional piece of it. All right. So IJKL is like this by Eisenhardt again, but this time n is equal to 3, so we get the 3 scalar over 6. And so contracting to get the Ricci tensor gives us this, but then the Gij is really gamma ik, so that contracts against this to give you the trace of gamma, which is 3 because we're in 3 dimensions. And then over here, this works out to Kronecker delta KL, which switches this K to an L. So I get JL for this. I get 3 of them here. I got -1. I got 2K gamma JL. And he also mentions, okay, so, well, let's think about it. If we're maximally symmetric, we're certainly going to be spherically symmetric. So all of that previous technology we had on the spherical symmetry back in the Schwarzschild solution comes to bear here. And so you can write d sigma squared as e to the 2 beta of r plus dr bar squared plus r bar squared d omega squared. And you can calculate, likewise, the components of the Ricci tensor with respect to this beta, like so. All right, lovely. All right, and then once you got all that, that gives you, putting things together here, this system of equations. 2k gamma 1 is the 1 component of the Ricci tensor, three-dimensional part of it, right? And that's equal to this. And so it's just putting the two things together. We have this equals this, this equals this, this equals that. And then Carol claims, and I don't see it when I wrote these notes, I still don't see it at the moment, that you can solve these and get beta is equal to -1/2 natural log of 1 minus k r bar squared. Now, once you have that, I understand everything that follows past that. So another homework problem for you. If you can see how to solve these to get that, I'd love to know. If you could figure that out. If you can't, it's cool, but give it a try. And so if we have that solution, we plug it into the e to the 2 beta right, from the last page. Yowzers. See, we're calculating the d sigma squared is e to the 2 beta dr bar squared plus r bar squared d omega squared. I'm putting in that beta solution that you're going to find in your homework because it's too hard for me. And so I get that minus, absorbing that makes it reciprocal. Then you got e to the natural log of the reciprocal, which pops the reciprocal back out like so. You plug that into the e to the 2 beta in the formula for the spherically symmetric 3 metric, and you get this, plus that. Now, k equals to 0 is what's called flat. K equals to 1 gives you the positive curvature. K equal to minus 1 gives you the negative curvature solutions. He then introduces a new radial coordinate chi, defined implicitly by d chi, is dr bar divided by the square root of 1 minus kappa r bar squared. And if you tilt your head and squint, you can integrate that thing. And depending on whether k is positive, negative, or 0, you get different integrals. So this is like calculus 2 right here, right? So you got all kinds of calculus 2 in here. So of course, if k is positive, that's an inverse sine. That's just inverse sine. You get whale. So you get x is equal to inverse sine of r bar, and then take sine of both sides to give r bar is equal to sine of x. Great. Now if kappa is minus 1, then it gives you 1 plus r bar squared. Well, the integral of the square root of 1 over the square root of 1 plus r bar squared is inverse hyperbolic sine of r bar. So if you didn't know that, well, then you probably should work on your hyperbolic calculus, right? We could all learn more. But anyway, so that these integrals are actually pretty clear. I mean, this is not complicated at all. This is just integration. So you get this, and this for your r bar, and then plugging that in gives us that. Well, then of course undoing by construction. Then this is dx bar squared. I mean d chi bar is d chi squared, right? And r bar, well, that is equal to s sub k, the scale factor for the k for k of chi d omega squared. And so there's your really nice formula for the spatial part of the maximally symmetric metric. And so let's see here. So what does that give us? Well, that gives us that a metric on spacetime with maximally symmetric hypersurfaces evolving in size can be written ds squared is minus dt squared plus this r squared t dr squared over 1 minus k r bar squared plus r bar squared d omega squared. This is the Robertson-Walker metric. Why is he giving up on the chi thing all of a sudden? I don't get it. Like he had that beautiful formula with chi, and then it's just gone. I don't get it. Well, whatever. I'm probably something lost in translation here. Probably if you go read Carroll, he's got more to say about that, and I just missed it. But my bad. Anyway, so back to the uglier version of it. Here we go. And he says you can normalize to make k either to minus 1, 0, or 1. Or you can introduce the scale factor, and then kappa, where it's k over r 0 squared, and then kappa can take any value. And then the Robertson-Walker metric looks like this. Carroll, he says he's going against the grain, and this is his preferred formulation of the Robertson-Walker metric, but whatever. I don't know. I'm not sure what the grain is we're going against, but if he says so, he's the expert. I will trust him. Let's see here. So from this, and this would be fun exercise, right? Straightforward, but tedious, I suppose. Here's your metric. So you can take the appropriate derivatives of those and their inverses, contracted appropriately as such. Calculate the Christoffel symbols, like so, right? And then you can use these to then calculate the Ricci tensor. Actually, next thing you'd do would be calculate the Riemann tensor, not even given. But you could use these to calculate the Riemann tensor and then contract the Riemann tensor to get the Ricci tensor, and then the Ricci scalar is this. So that's what it looks like. And then that brings us to the Friedmann equation, which is, so up to now we haven't really said anything about physics per se. We're just talking about the structure of maximally symmetric, in the spatial sense, spacetimes, right? And now he's like, okay, well, what is the stress-energy tensor's interplay with this geometry that we've just found? And so the stress-energy tensor, if we write it in terms of, the four velocity and the density and the pressure, I think, of dust here, we get this formula. And let's see here. Then looks at the raise the index, and I go through the details here. And so raising the index gets you a minus rho and ppp. And then if you take the trace of that, you get minus rho plus 3p. And he also explains that it has to be equal to 0 if you're dealing with electromagnetic radiation. So if that's equal to 0, that makes the radiation pressure equal to 1/3 the radiation density, energy density. And if you don't have a good intuition for that, then that's okay. You're not a physics major. You really shouldn't have a good intuition for that. I'm not sure how many physics majors have a good intuition for that, to be totally honest with you. But anyway, energy conservation is this, all right, this covariant derivative of the stress energy tensor with the index raised, right? And if you look at the 0th component of that, you get this thing. And then if you plug in the connection coefficients that we had on the last page, then allegedly you get to here. I think that's another good homework for you. Calculate these guys and verify the boxed equation here, because in Carroll these are missing. And I think that those are the missing links for understanding this calculation here. So if you do that, that would be healthy. Now if we set pressure equal to W times density, then the equation above simplifies to this. If that W, which is imposed for physical reasons, if that's a constant, then you can integrate this and you get that the density is like that. So I think we saw some of these formulas earlier in like chapter 4, where they were musing about the relation between density and pressure in different scenarios. Here's the proof that the trace of the electromagnetic stress energy tensor is 0. It's just a fun calculation, some more tensor arithmetic here. Here's your stress energy tensor by definition for the electromagnetism is this. And if I raise an index, then I get this, and I get, if I lower an index, right, lower the nu to a mu, then I contract over the mu, like so, beep bop boop. And over here, I contract the g over itself, actually, like that. But the meaning of this would be that, and that would be, because it's a metric and inverse metric, that's the Kronecker delta mu mu, but that's the trace of the 4-dimensional Kronecker delta, which gives you 4. So that simplifies to 4, and then you've got the same thing minus the same, you got thing minus thing, which is 0. Notice that this is just the notation, right? These are dummy indices of summation, so you can change, these are literally the same sums. So we used that in the previous page to find the formula for radiation density in terms of radiation pressure. So some other big comments here just to share with you, since we're looking at this book together. Carroll explains the scaling of matter and radiation. He says matter scales like 1 over the cube of the scale factor, whereas radiation scales like 1 over the 4th power of the scale factor. And measurements today suggest that the ratio of density of matter to the density of radiation is about 10 to the 3rd. So there's like 1,000 times more matter than radiation in terms of density. But if you could go back at earlier epoch, the radiation density would be dominating. And also something of note, the density corresponding to a cosmological constant or vacuum energy is proportional to a to the power 0. And he says many cosmologies become vacuum dominated if they don't eventually contract for example, de Sitter and anti-de Sitter spaces will be eventually, they'll be dominated by the vacuum energy. And so if we recall Einstein's equation like this, and we evaluate that at mu equal 0 or mu equal ij, we get these equations like so. And from those, you get, excuse me, goodness gracious. From those, we get the Friedmann's equation, which just relates the derivative of the scale factor to the density well, again, the scale factor squared here, right? And here's the second derivative of the scale factor. So he said this one's usually, when people refer to Friedmann's equation, Carroll says this is usually what they're talking about, whereas if they talk about the second equation, they're probably talking about this one. And then we introduce some rather well-known parameters to describe all this stuff, namely the Hubble parameter, which is the derivative of the scale factor divided by the scale factor. And there's also this Hubble distance and Hubble time. This, to me, I don't know what he's talking about, because I probably should look it up and sort it out, but I'm sorry, I'm just being lazy. But what do you mean kilometers divided by seconds divided by megaparsecs? Like, what exactly is going on here? I don't understand the units here. It doesn't make a bit of sense to me. But there it is, 70 plus or minus 10 kilometers second megaparsecs. Whatever that means. You can educate me in the comments if you want, guys. But anyway, so he also defines a deceleration parameter, which is in terms of second derivative of the scale factor divided by the derivative of the scale factor squared. And there's also this density parameter omega, which he defines by 8 pi g over 3h Hubble constant squared. Hubble constant's not a constant, by the way. And rho, and that's equal to the density divided by the critical density. And he says, in view of all this jargon, Friedmann's equation becomes omega minus 1 is equal to kappa divided by the Hubble constant, which is not a constant, squared times a squared. And so then you have this mishmash of ideas that you can use to describe the possible future evolution of the universe. If you believe this stuff, rho is less than, if the density is less than the critical density, that corresponds to the omega being less than 1, which corresponds to the kappa being less than 0, which corresponds to an open universe. On the other hand, if the rho is equal to the critical density, that it corresponds to omega equal to 1, which means the kappa is equal to 0, which means you're in a flat universe. And if the density is greater than the critical density, that corresponds to omega greater than 1, which means that your kappa is greater than 0, which means that you're talking about a closed universe. So I think, in some sense, the geometry is hyperbolic, it's Euclidean, and it's spherical in some sort of sense, like negative curvature, zero curvature, positive curvature. In any event, this much is known, that measurements put this omega very close to 1. And then, if you read Carroll, maybe the next 35 pages or so, page 340 to 374, concern the debate over the form of the yearly universe, including the add-on of inflation. So I think inflation is worth talking about for a second. So if you study these models, right, and you follow time back, the story basically goes something like this, right? There's at time 0, right? At time 0, there's a let me just scribble some things to try to hang my thoughts on this to make sure I don't miss something. So at time 0, t equals to 0, right? You've got some kind of bang, okay? And so, and then what happens is the universe unfolds, right, from that initial singularity, and it gets bigger, right? Well, maybe I should draw a sphere, I don't know. So maybe this is t equals to, I don't know, 3 minutes. And what kind of time we're talking about? We're talking about the time in the co-moving coordinate system, right? In one of these, in with respect to the you know um, Roberts and Walker metrics here, right? Um, Something like that. And so here, initially, you've just got this soup of radiation. All right, so it's incredibly dense, hot, right, etc. Right, and then so here, of course, time goes on, right, and then it gets bigger, right? It gets bigger, and at some point, it's as you're going on here, you're cooling, right? You're cooling as it expands, and at some point, this soup of radiation, it ceases being radiation. Particles start forming, right, from the radiation, and you start getting things that are matter, right? You start getting matter. So eventually, you freeze out. You freeze out matter. Things like that, right? And in that process, you also do things like you create the CMB, right? The cosmic microwave background radiation. All right. This was discovered by, what was his name? Penzias and I think Wilson, something like that. I don't know. I remember 1960, something like that. What was it? Oh goodness, I don't remember. I could look it up, but I'll say 1960 question mark, maybe 1961. I forget, something like that. And so in this process of cooling, right? And I don't know if you know this, but like in the process of things freezing, nothing. When something freezes, there has to be this change in the order parameter, and when you go from one phase of matter to another, there's the process of it actually changing from one phase to another. There's a whole discipline of physics devoted to understanding how that exactly works, and I'm not super well versed in that or anything, but there's sort of an expectation that if you freeze something, like parts of the things being froze on one side to another, there's some kind of communication of sorts going on there. So basically what happens, as I understand it, is if you look at the structure, and of course the other thing that's going on here is as it's cooling, it's expanding, and as that's happening, things are getting spread out. Right, so maybe you've got, let's just for the sake of discussion, suppose we've got like Bob here, right, and you got Jane here, and Bob and Jane are two bits of radiation, and they're doing their radiation dance, and they're bebopping around and annihilating and whatever radiation does when it's bored. It's got time to play around. So Bob and Jane, they as the universe expands, they're getting further and further apart, right? And then as the cooling happens, all of a sudden, eventually you reach this temperature, and then Bob and Jane no longer radiation. They coalesce into matter, and then there's a leftover radiation which freezes out this cosmic microwave background radiation, and it's done in such a way that basically when that freezing happens, there's this uniform ring, uniform cosmic background radiation that's everywhere. And this kind of begs the question, how did the order parameter communicate to these different places. See, because Bob and Jane at this point, they would be causally disconnected. All right, there's like, uh, in order for this, like they're well outside each other's light cones. I'm not sure I'm explaining this very well. The other thing, and so this is how Carroll seems to be explaining it, but um, the other book I read on inflation explained it in terms of large scale structure. He said that if you looked at the like large scale structure um, of I think distant galaxies, I want to say, or man, I can't remember exactly, but he said by looking at the large scale structure of the universe that there were things that appeared to have frozen out at an earlier time that shouldn't have been able to make patterns. Basically, the existence of the pattern in the sky suggested that there was superluminal communication of the things comprising that pattern if you went with the standard Big Bang timeline. So, the way to fix this is to say that this expansion that I'm talking about happening, right? This expansion that I'm talking about, the traditional, just uniform expansion rate, that was the original idea, something like that, is wrong because it doesn't match experimental verification. So instead of doing this, so the original was this uniform expansion from initial singularity. That was the original story, which fell out of favor in about the late 70s or so. So around 1978 or so, Alan Guth and others. There's a Russian who's probably equally responsible for these ideas that I can't remember the name of off the top of my head. Fill in blank. Invented what's known as inflationary cosmology. Inflationary cosmology. So the idea of inflationary cosmology is that early on in this, in this process, like this time, this era, maybe the first couple minutes of the universe, I forget the details, all right? And I think the details are debatable. I mean, when I asked my general relativity professor at Stony Brook about inflationary cosmology, he asked me, well, which one? There's like 150 theories. And that was in 2001. So I'm not sure if the situation has gotten better. I think that Carroll does a pretty good job of sort of summarizing the main features in his book, all right? But basically, the idea of inflationary cosmology is that there exists an inflaton field. All right, and this inflaton field, what it does is it couples to the universe, right? And what it does is it dumps all of its energy into the expansion of the universe, essentially. So what happens is, as this inflation field inflates the universe, right, the universe expands from like nothing to something like, usually the thing you hear is like e to the 60th. So it basically goes from nothing to incredible expanse in an instant. And this is necessary to suppose this, to deal with observations of cosmology. So it's interesting. The process of inflation basically it has the effect of sort of hiding the initial condition of the universe, because that process of inflation is kind of violent. And so you see things after the inflation, but not before, really. But then Carroll also explains how it does tie into certain, grand unified theories and other things. There is something about this inflation and how it links together with these standard cosmologies that perhaps gives us some sort of window of insight into energies of the like 10 to the 15th to 10 to the 16th GeV, something like that, which is like well, well outside the range of observational high energy physics, I think. Let's see here. What does he say? Where is it? Now, he claims that, 10 to the 16th GeVs. Now, Carroll says that the reason for the inflation is, to solve the flatness problem and something else. But I think, well, I mean, fine, but the fact of the matter is that without inflation, standard uniform expansion, Big Bang, general relativity is at odds with observations. So essentially you're driven, here's my view, you're driven to say something that, golly, it looks an awful lot like what's described in Genesis, from something, from nothing to something, and in an instant, everywhere, all at once. Now, I'm not going to try to sell you that, the details of the traditional secular story in terms of how stars evolved and all those sorts of things are in line with Genesis. I don't think that they quite are, and I think that's because they're wrong. So, but anyway, exactly why they're wrong and how they're wrong, well, that's anybody's guess. But I do find it amusing that at least, we've gone from the preference of, having having a universe without a beginning, like, oh no, that doesn't work. We need a beginning with the Hubble. So that was the early discoveries, the discovery of redshift in terms of those the redshift observations, I believe, predate the cosmic microwave background radiation. And then, then being pushed further to say, well, not only is it expanding from an initial singularity, it has to have done so in a rapid and essentially, instantaneous fashion. Man, that is, if that's not close to what is written in Genesis, I don't know what is. But in any event, there are, of course, genuine differences between the scientific, the secular science creation myth versus what's found in Genesis, and I don't think we do anyone favors when we try to pretend that there aren't differences. There are differences, and it's a question of what you think is more trustable, I suppose. But anyway, I guess that's it for cosmology. There's some larger points here, which is, like, what if the universe is finite? That changes things, I think, in all this story. If the universe is not, if the Copernican principle is actually wrong, if there actually is a finite extent to the universe, how exactly does that impact things? Man, there's so many different things to think about. But anyway, I am not an expert. I'm just telling you what little I know here, and I'll stop it here. So, next up, we'll do something, I think, which is more fun, which is Appendix J. So that's my next thing here would be Appendix J, which is on non-coordinate basis. So we'll see what that takes us. But anyway, I think I'll stop here for now. So thanks, guys.